So we're going to be talking about experiment 13 this week, which deals with the nitration of a benzene ring. So we're going to be dealing with electrophilic aromatic substitution. First, I want to quickly review the general electrophilic aromatic substitution mechanism. And I want to emphasize it doesn't matter what your electrophile is in this particular case, the mechanism is exactly the same. What's important is how we actually generate the electrophile. But first, let's talk about this general mechanism where we have some electrophile, in this case E+, we're just going to use the generic E+ type approach here, and we've got an unsubstituted benzene ring. So of course the E+ is a Lewis acid, it's electron deficient. And in this case we're going to have the benzene ring actually function as a Lewis base, as an electron pair donor. Now we know that aromatic rings, especially benzene, are more stable than one would predict. That's why we call them aromatic. And what happens in this particular case is one of the pairs of electrons from the pi system attacks the electrophile. It being electron deficient, it wants electrons. And in doing that, what we've generated is what's known as an rhenium ion, which is no longer aromatic. So it's actually higher in energy than the starting materials. However, it is resonance stabilized. We can draw a number of resonance structures for that particular rhenium ion, and I'm going to hold you responsible for actually knowing how to draw those individual resonance structures at this point. However, since this is unstable, it would like to get back to an aromatic system. It can either lose the electrophile and go back to starting material, or the counter ion of our electrophile can actually come in and abstract the hydrogen that's on the carbon also containing the electrophile now, and those electrons can go to the carbocation, regenerating the aromatic system. And so basically what we've done is we've substituted the electrophile for the hydrogen at that carbon using this mechanism. And we can use a whole series of electrophiles. We've talked about these in class, but in this particular laboratory we're going to use NO2+, so we're going to do a nitration. And so we need to know how to generate NO2+. And the way that we generate that is by using a mixture of nitric acid and sulfuric acid. Works pretty well to make the NO2+ electrophile. So I'm going to draw out nitric acid in its proper Lewis form. So there we have nitric acid, and we've got sulfuric acid. So I've just drawn it out a little differently than probably how you're used to seeing it. We're only interested in one of the acidic hydrogens here. And it turns out that sulfuric acid is more acidic than nitric acid. So in this case, nitric acid is going to function as a Lewis base, which is a little counterintuitive to most people. It is an acid after all. However, we have to compare them to one another. And so the sulfuric acid is going to be our Lewis acid. And what happens is we protonate the nitric acid at the oxygen bearing the hydrogen. And now we've got our protonated nitric acid. This looks like water, which makes a very good leaving group. And that's how we generate our NO2+ in this particular reaction. And so this is now our E+ for what we're going to be talking about in dealing with in this laboratory. Now in this laboratory, we're going to be dealing with a competitive nitration. So you're going to start off with equimolar amounts of methyl benzoate and acetinolide. And you're going to react these with our NO2 plus. And you're going to see which one you get. Now, of course, methyl benzoate has an electron withdrawing group on it, and so it's a meta-director. So the product that one would get from nitration of that would be the meta substitution pattern. However, this one is an ortho-para-director because the atom directly attached to the benzene ring has a lone pair of electrons. And so what we would get from there is a mixture of ortho and para plus the ortho isomer. But we'd only get a small amount of that. It's actually the para that's the one that forms in greatest quantity. These obviously are different molecules, and so they will have different physical properties. You're going to recrystallize whatever it is that you get, and you're going to determine which one of these you got based on melting points. Now, it's very important that you look up before you come to class the melting points of this compound and this para compound by going to the Sigma Aldrich website. They're available there. But it's your responsibility to come to lab with that information in hand. So once you have the melting points, you'll be able to determine which molecule we made, and you'll be able to determine which one of these groups is activating and which one of these groups is deactivating based on this. So we're basically doing a competition experiment. Remember, an activating group is anything that makes the reaction go faster than benzene, and a deactivating group is anything that makes the reaction go slower than if we were doing the reaction with benzene. So electron withdrawing groups are deactivating. Electron donating groups are known as activating groups. And so this reaction that I've shown you down here should be the one that goes the fastest and the one that you get the product from, whereas the one up here at top is deactivated and should actually occur at a much slower rate than this one. So this week, very important, make sure you get those melting points before you come to lab, and make sure you read your chapter on electrophilic aromatic substitution so that you understand exactly what it is that we're doing in lab, and realize that one could do this with more than just nitration, but generating the NO2 plus is quite easy from relatively inexpensive starting materials like nitric and sulfuric acids, and that's why we've chosen to do the nitration over the other possible electrophilic aromatic substitution.